in the national grid. Once in my car, everybody recognises a sat-nav. But what about the fuel I use? My lottery ticket? Even the train I catch? All increasingly depend on satellites. Trains, planes and automobiles. Shipping, cereals and flooding. It's not even 9 in the morning, and already I've used nearly 40 satellites. These are the satellites that have changed our lives. But what about those that are changing our understanding of the universe?
This is a full-scale model of the James Webb Space Telescope. When the real thing is launched around 2018, it will be the largest, most powerful satellite telescope ever built. With it, we'll be able to see wider, deeper, and more clearly into space than ever before. We may even be able to look back to the very birth of the universe.
For several years, my job has been to work on the special cameras that will allow the James Webb to peer deep into the cosmos. By capturing images of stars 13 billion light years away, it'll look back in time, helping reveal how the universe itself was created. I believe that James Webb and the countless satellites that dominate our day are amongst the greatest scientific achievements of our age, and sit at the cutting edge of technology.
We're going to look at the breakthroughs that make this remarkable machine possible. What were the scientific challenges that we'll face in the satellite revolution?
And in the early days, there was one problem above all that space scientists wanted to solve. How do you get something, anything, to hover in space above the Earth?
Well, a good place to answer that question is here, by this lake.
A beautiful spot to try and launch my own satellite. Three, 2, 1.
Fire!
The force of gravity has, of course, pulled my wannabe satellite back to Earth.
What goes up always comes down. Or does it? As we all know, the Earth is round. And that means, as we travel over the surface, it gently curves away from us. Now, if we can travel fast enough, something miraculous happens. We keep on falling, but we never hit the ground. Let's imagine that I can launch this orange at incredible speeds.
It's something Sir Isaac Newton noticed 300 years ago. Relative to something moving horizontally, the curve of the Earth makes the ground beneath drop away. If my orange, or anything else, can move fast enough, it can stay ahead of that curve and effectively outrun gravity. It'll never fall to Earth.
Because the curvature of the Earth is quite slight, you need to be travelling at around 8,000 metres per second to compensate for that pull of the Earth's gravity. If you can reach this speed, you're now travelling around the Earth rather than down towards it.
Not easy, of course, when there's air resistance to slow you down and obstacles to get in the way.
But once you get above the mountains and most of the atmosphere, at say 300 kilometres up, you are now in space. And if you can keep your ball travelling fast enough, you can stay ahead of the curve. You're in orbit.
Well, that's the theory. But it took 250 years after Newton's death before anyone built a machine powerful enough to put it into practice. In 1957, a Russian rocket carried the first man-made object into orbit above the Earth. No bigger than a beach ball, Sputnik stayed in orbit for 3 months. For the Soviet Union, it was a massive propaganda victory. And the beep of its tiny radio transmitter fired the starting gun for the space race.
I have always assumed that as Sputnik was dragged into a lower and lower orbit, it got hotter and hotter due to the Earth's atmosphere and was eventually completely burnt up. But surprisingly, a small piece of that epic spacecraft is kept here at the Smithsonian National Air and Space Museum. So I hear you have a bit of Sputnik actually here on site.
We do indeed. We have something that is called the firing pin, which is a relatively small object that is not really a firing pin in any real sense of the term. That implies that you launch a rocket by turning a key or something. But what it really was a small metal object that fit into the Sputnik spacecraft. And when you were ready to start the system inside that was run by batteries, you could pull this out and it would complete the circuit that would allow the power systems to start to operate.
So it's like when I buy a little toy, sometimes I have a little plastic tag, pull it out and the batteries start working.
That's essentially what it was.
The firing pin is a tangible reminder of who won the race into space. It may be small, but to me, it is a priceless relic, which, by making the connection between the battery and the transmitter, unlocked the age of satellites. But it wasn't easy. Desperate to catch up in the space race, it took the Americans years of rocket research and numerous false starts, before finally they successfully launched their first satellite, Explorer 1. In 1959, Explorer 6 was the first satellite to take a picture of the Earth. It doesn't look like much, but it was enough to get one group of people very, very excited. Spies. By the end of the 1950s, the Cold War was hotting up. Satellites would allow Soviet and American spies to photograph each other from a perfect overhead viewpoint. The Americans quickly launched the world's first spy satellites, codenamed Corona. But now the spies had to get their film back to Earth, and their solution was about as bonkers as you can imagine. They threw them back. This remarkable footage shows a canister carrying thousands of meters of used film being ejected from a Corona spy satellite 200 kilometers above the Earth. 18 kilometers up, its parachute opens. Having spent countless millions launching spy satellites, the Americans now had to catch the results mid-air before the Russians could reach them. This is 037, one of the planes that attempted those difficult, dangerous, and highly secret missions. Bob Counts clocked 2,000 hours as 037's navigator. He had the almost impossible task of spotting the canister falling to Earth, then plucking it out of the sky somewhere over the Pacific.
Bob, this is one of the aircraft that actually caught films from space.
Yes, it's not one of them, it is the very one. Well, it's one of 9 that we had, but it's the aircraft that caught the first one.
So what sort of range did the aircraft have?
Well, its range was 2,000 miles, which was a little bit of a handicap because we had to operate way at the edge of its endurance on many of the missions.
Bob and his team were attempting the equivalent of finding a needle in a falling haystack. This declassified footage shows the crew of 037 closing in on their target. First, the crew suspended a line between 2 poles hanging from the back of their plane. Dangling off it are grappling hooks.
The aircraft would match its descent rate with the descent of the parachute and flying right over the chute, like 5 feet over the chute, bringing the parachute between those 2 poles into this array of line and grapple hooks.
First time, it's a miss. Then, success. But this was also a remarkable historic first.
This fellow here, that's Algene Harmon, and he was in charge of the pole handlers of the recovery crew. And as they reeled in the capsule, there comes a time when somebody has to lean out and physically grab it
and bring it on board the airplane, and that was one of his jobs. As it came up to the tail, finally it was close enough, so he reached out to grab it, and when he touched it, he jumped back and let his hands loose because it was hot, and he didn't expect that, coming from stratosphere, whatever. He thought it was going to be cold, but he reached back out and got it and brought it on board. But that means that he was the first human to ever feel the heat of re-entry.
Yes. An unsung hero.
We're all unsung heroes.
144 Corona satellites were launched in all, taking hundreds of thousands of photographs of Soviet air bases, bombers, and rocket launch pads, as well as Chinese nuclear test sites. It transformed the American military's understanding of its Cold War opposition. But Corona was cancelled shortly after a Soviet submarine was spotted beneath a mid-air drop zone. Catching canisters of falling film wasn't just difficult and dangerous, it was now compromised. There had to be a better way to get images back from space. This is a silicon chip. But not any old chip. When this device was invented, it totally revolutionized the world of spy satellites. It's called a charge-coupled device, a CCD. At its heart is a thin sheet of silicon, which has an unusual property. It's sensitive to light. So if a passing photon hits it, it takes that photon and creates an electron, which can then be stored. This means it can generate a picture of anything that's in its field of view. It changed the rules of the game. The invention of the CCD in the 1970s allowed satellites to take pictures, store them electronically, then transmit them back to Earth using radio waves. Today, intelligence agencies don't reveal how powerful their spy satellites are, but some details have leaked out. In 2007, it was revealed US satellites had been targeting American territory. In fact, the Super Bowl. US counter-terrorism wanted to monitor potential internal threats. The real photographs have never been released. They're just too sensitive. But it shows the resolution is now powerful enough to see objects and individuals down to a few centimeters. But spying was just the start, because civilian scientists also began using this new imaging technology, transforming our knowledge of the Earth. It led, of course, to breakthroughs in our understanding of the weather, the shrinking of the ice caps, and the effect of cities on our environment. Images that have revealed the full wonder of our planet. Today, satellite images are everywhere and available to anyone at the click of a mouse or the touch of a phone. It's opened up whole new areas of information and research. But the sheer mass of data sometimes creates its own challenges. Dr. Albert Lin is using satellite imagery to explore a remote part of Outer Mongolia. He's searching for the tomb of one of history's most infamous leaders, the Mongol warlord Genghis Khan. His detailed satellite imagery spans an area of more than 10,000 square kilometers. But surveying this virtual landscape is almost as hard as exploring the real thing.
And we're looking at examples like this, where you've got roads, you've got rivers, and you've got these features, right? And when you look at it, you say, okay, well, each one of these pixels shows me something. This is the wall of the building. You can tell it's man-made. You can tell that this is modern. But there's also this other feature here that looks similarly not natural. It looks strange, right? Like these little dots here and these mounds there. They look like they may be something that was made by people. But they look different than this. And what about them looks different? It's hard to describe in words. It's hard to quantify. But something about it looks ancient. It looks more worn down.
I would pick that out as something of interest at least.
Right.
Computers can't recognize the features on a satellite image that could be ancient ruins. So all 10,000 square kilometers need examination by human eye. It's a seemingly impossible task. But the team's solution is ingenious. Dr. Lin has enlisted the help of thousands of human volunteers. He's broken the vast satellite images into countless smaller ones. them on a website and invited anyone to join the digital expedition. If someone sees anything interesting, they mark it. An agreement starts to emerge about what's worth exploring.
This is an example of a lot of human consensus saying, I see something weird there. I really see something weird there. You should go check it out. Well, now let's take a little look closer.
So we're zooming in again.
Yeah, it looks a little bit, big, it looks weird, it looks rectangular, but when you actually look at it in the context of the other data around it, you see that it's actually right next to these little dots here. When we went out and explored this area, it turns out that those little dots are people's homes. They're their yurts. And when we found this thing, it turns out that it was actually this ancient fortress. Now, it might not be the tomb, but it's definitely a clue.
Albert Lynn and his volunteer force of armchair explorers have yet to find Genghis Khan's tomb. But I find his work a comforting reminder that even the most powerful technology can't always better our human judgment. CCDs have transformed not only what we take in when we look down at our planet, but also what we see when we face outwards. This will be James Webb's task when it's launched in 2018. It'll be glimpsing galaxies that are almost unimaginably distant, 13 billion light years away.
How do you capture the intimate detail of a galaxy spread over millions of light years? Well, the vital component for the James Webb is its gigantic golden mirror.
And it's not just size. To see into the depths of space, scientists have had to take mirror technology to a remarkable new level. One part, above all, is crucial for the mirrors on space telescopes: their coating. This is what does the actual reflecting.
As a space scientist, I've seen many mirrors coated in the past. But the people who've been given the daunting task of coating the James Webb mirrors are the technicians here at Quantum Coatings in New Jersey. And I'm about to find out how they do it.
The mirrors have to be perfect. The tiniest speck of dust could be disastrous. So Quantum's lab is one of the cleanest rooms in the world, more spotless even than a hospital operating theatre. This hexagonal pane of glass is an exact template of the metal sheets that will make up the James Webb's mirror. They're made of beryllium, a very rare and extremely strong and lightweight metal.
That gun has dry ionized nitrogen gas. He's blowing the surface off. So this is our last chance to blow off any last remaining particles before it goes in the chamber.
The glass is then carefully placed in a large vacuum chamber.
The mirror's in there now, everything's ready to go, and I've got a pleasure of shutting the door.
For 2 hours, all the air and any remnants of dust are extracted from the chamber, until finally the gold is added. Gold is used for the coating because it reflects infrared light so well, the part of the spectrum the James Webb cameras use for imaging. First, it's heated with a laser, vaporizing it.
How much gold are we talking?
The amount of gold that we evaporate is about 40 grams. The amount that gets onto the mirror is a quarter of that, just a few grams.
You must be talking about a fairly thin coating of gold.
To put it in perspective, one sheet of paper is about 1/1000 of an inch thick. We could fit 100 gold coatings into that piece of paper.
It's a single piece of paper.
That's right.
The result? One of the most perfect mirrors on Earth.
So here we are.
Wow. That is lovely. It's beautiful. It's just so smooth. I think I've never seen my reflection so clearly. I think the fantastic thing is the idea that this coating is going to be out in space. And on sort of 18 mirrors like this. It's quite phenomenal.
It's quite a thought.
The 18 mirrors are hexagonal because they fit together more snugly than if curved. The hexagons also form a shape that is roughly circular, so focus the light evenly. These mirrors are typical of the James Webb. Every aspect of its engineering has been pushed to the limits of what's technologically possible. Yet, there's a strange irony. To launch it, we will rely on the same basic technology that got Sputnik into orbit half a century ago. A rocket. With a payload space that's not much bigger. Yet the James Webb has huge solar panels and a sun shield to protect its delicate instruments that's 5 layers thick. It's all very bulky.
So how do you squeeze something as large as this into a rocket with a carry capacity the size of a school bus?
The answer is origami. The creator of this miniature theme park is Dr. Robert Lang. And surprisingly, his origami skills have been invaluable to NASA's space program. Because the Japanese art of origami lets you turn something very large into something very small.
This is the pattern that I just folded. It's called the Miura Ori, and it was discovered by Koryo Miura, a Japanese engineer working in the Japanese space program. He was studying the way thin plates buckle under stress, and that led him to discover this fold pattern. And he explored it and found it had a really nice property. It opens and closes with all of the folds happening together because they're mechanically linked. Then you would only need to bend a single fold to make the entire structure open and close.
So when you open one fold, all the other folds follow and you flatten out.
So if this were a solar array in space, you'd only need to put one solenoid or mechanical mechanism on, one fold, and that fold would be enough to make the whole thing open up.
Robert offers to show me how to make something the size of a solar panel fit into a small payload bay. The sheet is 9 square meters, and its transformation will involve 72 separate folds. Robert pre-creases the folds to increase accuracy and flexibility.
Wow, that's from the spiral.
Yep.
Origami may be Japanese, but I never expected it to be a martial art. It certainly needs 1 or 2 ninja moves.
All right.
So you've taken that huge piece of paper and reduced it to this.
That's right. So if this had been a solar array, we've taken it down to the size it could go into a rocket. Goes up in space, opens up, and then it's ready to deploy back to its original flat state. We've gone down by just about a factor of 100, about 10 in each linear dimension. And of course we got that by going from completely flat to a vertical tube like this.
But much easier to sew in a rocket.
Exactly.
Robert's creation is clever enough, but the real revelation comes with its opening. Although the design appears complex, because it was folded along one axis, the whole sun shield can be opened with a single motor. This animation shows how, in 1995, Japanese scientists used the same trick to fold a large solar panel on a satellite called the Spaceflight Unit. It's the brilliant application of 17th century Japanese art to a very modern Western technology. The ability of satellites to have these large structures gives them, quite literally, their most eye-catching feature. It means we can see them from the Earth.
Oh, I can see 2 flashing things, but I think they're both aeroplanes. And something else flashing over there.
I am with a group of brownies trying to spot satellites in the early evening sky.
Now we don't just look this way, we've got to look all across the sky. Let's try and take it all in. I can see the maze, I can see 2 of them.
On average, 2 satellites pass over Britain every quarter of an hour. But they're not the easiest things to see.
Now what are you looking for? Well, you're looking for something that looks a bit like an aeroplane, but it's not going to flash, and it's going to move slowly across the sky.
Tonight, my team of brownies is in for a treat. Because the biggest satellite of them all is due to pass directly over Hatfield. It's The International Space Station, the largest thing human beings have ever put into orbit. It took more than 12 years and 30 trips to build, and it circles the Earth nearly 16 times a day. Everyone, including the astronomers with their telescopes, is waiting for it to appear over the horizon.
Oh, I can see a star moving really, really quickly. Oh, no, I don't think that's a star moving, that's a space station. I didn't say it. That is the International Space Station.
There's a crude rule of thumb. If a satellite orbits 300 kilometers up, it needs to be just 1 square meter for us to see it with the naked eye. The ISS has 8 solar arrays, each 17 meters long, so with a pair of binoculars you can see it from Earth in wonderful detail.
You look anything else? That's still the space station, so it's gone all the way from over there, up above our heads, and now it's heading over there. And you see it's still moving slowly.
Like many satellites, the ISS is only visible for a few minutes before it disappears over the horizon.
I think it's gone now. I know, but you literally saw it.
In the early days of satellites, this vanishing act was as frustrating to their engineers and controllers as it was for our brownies. It meant that the opportunity to transmit a signal, like a television picture, back to a particular point on Earth was very brief, maybe only lasting a few minutes. So the dream of the first satellite engineers was to have a satellite that stayed stationary above a single point on the Earth, allowing them to transmit information whenever they wanted.
So how do you keep an orbiting satellite hovering above a single point over a rotating planet? Well, it seems simple. You just slow your satellite down until it's above the point you want. But unfortunately, it's a lot harder than it sounds. And to show you, I'm going to use this carousel.
Imagine it's the Earth, spinning on its axis. And let's say I'm a satellite, orbiting it. If I start slowing down to be above just one place, I'm not going fast enough to stay in orbit. So I start spiralling down towards the Earth. And eventually, I burn up in the atmosphere.
There is a solution. The further I get away from the Earth, the weaker the effect of gravity, the less it pulls me back. And there is a magical point where the force of gravity is so weak that I can travel fast enough to stay in orbit, but also slowly enough to match the speed of a single point on the Earth's surface below.
Scientists calculated that this is nearly 36,000 kilometers away. Orbit here, and you can stay above the same point on Earth.
You are now in a geostationary orbit. And when this was first achieved, it triggered a revolution. Because now, any time, day or night, you can beam information back to Earth. This was the birth of the communications satellite.
It meant that with as few as 3 geostationary satellites, you could beam a signal around the planet, broadcasting it to almost anyone. The first satellite to relay a television signal was Telstar in 1962.
Here we are. There's a bar. Now we are anticipating. That's a man's face. There it is. There it is.
Its first broadcast lasted just 19 minutes. But within a few years, a network of geostationary satellites meant live communication was possible anytime or any place on Earth.
In the end, when there are more satellites still, you'll have television and telephones all over the globe, a shattering thought.
Broadcast television had created a global living room with shared experiences and values.
Junior, go with Bravo.
It also meant that as well as recording events, satellite broadcasts were now helping to cause them. Like the protests in Tiananmen Square, the fall of the Berlin Wall, or the Arab Spring. Today, nearly 200 communication satellites are broadcasting back to Earth, most in geostationary orbit. But staying 35,786 kilometers above a single place on Earth isn't easy. Satellites tend to drift. So to keep them in position, you need a technology that reached its pinnacle with Saturn V. The most powerful rocket ever built. But rocket thrusters don't all need to be like this. To keep a satellite, like the James Webb in orbit for instance, you need thruster technology that's far more precise.
Despite being the size of a tennis court and weighing over 6 tons, the James Webb Space Telescope will use microthrusters the size of a coffee cup. How is this possible? Well, it's due to the microgravity vacuum environment of space. With virtually no air resistance or drag, it can take a tiny force to move a very large object.
Engineers here at the Massachusetts Institute of Technology are at the cutting edge of thruster engineering, taking them to a new level of precision. Here in the lab, they've got an unusual way of recreating the frictionless conditions of space. They're using a tabletop and mini satellites called spheres.
We have a very smooth surface, and we also have these air carriages, which are little structures that we put underneath the satellite that have CO2 attached to them in these tanks, and we use them a lot like an air hockey table.
So can I see them in action?
Sure, absolutely. And so your job is going to be to fly this satellite, which is sitting right here, all the way over and dock with this satellite.
I'm not a very good games player, so I'm a bit nervous now. Let me put this down here.
Okay, twist the controller.
Whoa!
The microthrusters on the spheres shoot compressed carbon dioxide. It's colourless, but strips of tinsel show when they're firing.
So that would give me some twist.
Yes, exactly.
So I could do a dance.
Yes, exactly.
Try to... Okay. Now which way?
Okay.
Look,
That's
way.
one of the other hard things, to figure out which
as
way.
I spin, I lose my orientation. Oh yeah, and it just keeps on going, doesn't it? Uh-oh.
Fire a thruster, and just like in space, your satellite shoots off in the opposite direction, with nothing to stop it. Imagine how hard it is in 3 dimensions. So far, they've tested the spheres on board the ISS. It shows that their thrusters are so precise, the spheres can fly in close formation. The next step is to build satellites that can do this in open orbit.
There you go. That's a good trajectory. Now, don't build up too much speed there. Hooray!
Toss!
This ability to keep satellites in one position and know where they are is now remarkably accurate. But it's had a surprising side effect, because it means we can also know our position extremely accurately. The story begins back in 1957, shortly after Sputnik was sent into orbit. The sound of any object changes as it moves past us. While Sputnik was orbiting, American scientists realized they could use this knowledge to locate it, listening to the changing sound of its beam as it moved overhead.
It got scientists thinking. If you could work out the position of the satellite from here on the ground, could you reverse the process? Could you use the satellite's known location to find your unknown one?
The result was the Global Positioning System, or GPS. And how it works is simpler than you'd think.
It's all due to one of these. The breakthrough technology that led to GPS was actually a clock. Well, not any old ticker. This is an atomic clock, the most accurate timekeeping device ever built. For instance, if I set one of these going at the time of the Big Bang and let it run through, we would now know the age of the universe to within a few days. Now, compare that with a quartz watch, and we'd be out by 150,000 years. Atomic clocks are so crucial to GPS because the first stage in working out your position using a satellite is to know exactly where the satellite is. And the best way to do that is using time.
Each GPS satellite broadcasts a signal with a timestamp. It takes the signal just a fraction of a second to travel to your GPS receiver back on Earth. When it arrives, the receiver's clock works out how much earlier the signal was sent. Knowing this time difference means it can then work out how long it's taken to arrive, and so how far away the satellite is. But it doesn't just do this for one satellite, it does it for at least 4. Having calculated how far away each is, your receiver then creates spheres of distance around you. And where they intersect is where you are. There are 31 GPS satellites in all, and the more you are in contact with, the more accurate your reading. It means wherever we are in the world, GPS can tell us our position within a few meters. But increasingly, GPS can also tell us what the planet is about to do. I come to Japan, to Mount Uzu. It's one of the country's most impressive natural wonders. But it's also a time bomb. Because Uzu is a volcano. In the past, any volcanic activity here has usually been seen as a false alarm. The locals tend to ignore it and stay put. But when in March 2000, Uzu shook with earth tremors, scientists insisted 16,000 reluctant locals were evacuated. Within days, a huge eruption spewed large amounts of ash and mud down the volcano, destroying a hospital, a school, and hundreds of homes. Yet, not a single person died. The reason scientists were so worried this time was partly thanks to GPS. This is one of a network of GPS stations around Uzu that played a key role in saving so many lives. Over 48 hours at the end of March 2000, the distance between 2 of these stations increased by 2 centimeters. It doesn't sound much, but for the volcano experts, it was a signal that huge forces were building beneath the surface, and it helped them to decide to order an evacuation.
それは今までの歴史的な噴火が全てそうだったからです。そのために、ウッサンの噴火予知では、より正確な噴火時間とどこから噴火するかということを予知することが必要になります。やっぱり、GPS は強力な道具の一つだと思います。
But of course, volcanoes aren't the only natural disaster that struck Japan. Last year, the country was devastated by the Tohoku earthquake. It was one of the worst in the country's history, triggering a tsunami that reached 40 meters high. Nearly 20,000 people lost their lives. It's hard to believe this was once a school. Yet despite the fact a GPS receiver stands in the grounds on the front line of the devastation, GPS technology couldn't predict the earthquake. Even though GPS can measure the surface of the Earth in great detail, it cannot predict tectonic shifts beneath the ground. It can tell us what has happened, not what is about to happen. Or that's what we thought. Professor Kazuki Heiki analyzes GPS signals, but he's not working out his location. He tries to work out why they fluctuate. He measures how much GPS is disrupted by electrons in the atmosphere. It's called the TEC, or Total Electron Content. Professor Heiki has been studying how, after big earthquakes, rumbling sound waves disrupt GPS signals. But in the days after the Tohoku earthquake, he noticed something unexpected. He discovered a strange disruption in the GPS signals before the earthquake happened.
I want to understand what's happening with this phenomena. So can you show me a curve of what's happening with no earthquake and what's happening if an earthquake is coming?
Okay, so let's assume this is TC.
TC, that's the number of electrons
That's right.
in the ionosphere, about
Yes.
300 kilometers up.
Yes.
Okay.
And this is time. And if there's no earthquake, it behaves like a smooth curve, like this.
Why do we get that strange curve? Why isn't it flat?
Because of the movement of the GPS satellite in the sky. So this is a kind of apparent movement, apparent change.
So when it goes through a thick bit of atmosphere,
Yeah.
you get more electrons.
That's right.
As it's straight overhead, you get fewer electrons.
Yes.
And then again, you get a thick bit.
Yeah,
Okay, that makes sense. So you get a curve.
Yes.
So that's if no earthquake's going to happen.
And if there's an earthquake here, for example,
So that's the earthquake.
yeah, this is the earthquake. Then it will leave the normal curve about 1 hour before the earthquake, like this. And there's a disturbance caused by the sound wave.
So it suddenly seems, from this curve, because it's higher than this one, you're getting more electrons in the atmosphere.
That's right.
That seems strange. You've got an earthquake coming, and suddenly you're getting more electrons in the atmosphere.
Yeah, that's a very strange phenomenon. So
It's thought that in the lead up to an earthquake, forces deep underground somehow energize electrons high in the atmosphere, which in turn disrupts GPS signals. And Heikki has noticed this has also happened before other earthquakes too, like Chile in 2010. It's a remarkable discovery, which at the moment scientists don't fully understand. But it offers hope that one day GPS will act as an earthquake predictor, saving countless lives. For half a century, satellites have been at the cutting edge of technological advance, driving rocket design, revolutionizing how we view the planet, transforming our ability to communicate, and even to know where we are. But now, in the early 21st century, this technology is becoming far simpler and smaller. Satellites are no longer just for big governments and powerful corporations. They're becoming almost personal. And tonight, I've got a front row seat to discover how.
Here, in the Vandenberg Air Force Base in California, scientists are taking the next leap forward in satellite technology. Inside the tip of the rocket, situated over there, are some of the first new prototypes in the personal satellite revolution. They're called CubeSats, and they look like this. 5 of these satellites will all be released into orbit, hundreds of miles above our heads, like a flock of strange alien birds circling the Earth.
They're owned mostly by universities and will join the 40 or so other CubeSats already in orbit. They do everything from measuring radiation in the solar system to studying bacteria in space. Surprisingly, one country at the forefront of CubeSat technology is Britain. Here, engineers have devised one of the most imaginative uses of them so far.
That bit in the centre is the CubeSat, so do all of CubeSats have these sails as well?
This is a particular mission. It's called CubeSail. One of the big hot topics at the moment is space debris. Okay, there's lots of debris up in space. So if we can attach these CubeSats to bits of debris, maybe they be old satellites or old parts of launchers which are still orbiting up there, if we can attach these CubeSats to them, open up the solar sails and allow them to literally drag them back into orbit and burn up in a safe manner, it means we're decluttering space.
Because I must admit, one of my fears with CubeSats is the idea of all these sort of little things floating around in space causing more space debris. But this is actually helping to solve the problem.
Yes, very much so indeed.
Yeah, very neat.
Thank you.
CubeSat